it is my pleasure to introduce our next speaker from the Department of Mechanical Engineering. So one of the things I'm really excited about with this symposium is the fact that it's so interdisciplinary, and it's grabbing people from across campus, but then also we have speakers from Michigan State, so other campuses as well. Along those lines, happy to introduce our next speaker, Dr. Jesse Capecelatro. Dr. Capecelatro's research group develops numerical methods and data-driven approaches for the prediction and optimization of messy turbulent flows relevant to energy and the environment. And the pandemic has really shed new light on all of the complexities surrounding how viruses move through our environment. I never thought I'd see a debate on droplet size in the New York Times. And so I'm really excited to hear along these lines how Dr. Capecelatro's work in this area informs how we think about the pandemic and mitigation. So take it away.
Great, thanks. I really, it's great to be here. It's not every day I get to speak to an audience like this, and especially a session introduced by the President Schlitzel. And I really enjoyed Marissa's talk, and at the end she mentioned there's this sort of fine line between simple models, because we as we saw earlier this morning, when we want to assess risk, we need to run many of these models. So we need things that are fast and be able to change parameters. And so part of what I'm going to show here is that other extreme. What if we really do a deep dive and look at sort of more complicated models that are not very fast, meaning we're running on supercomputers for many days? What might we be able to learn from that? But then going from there, looking at moving up to larger scales, so we can start getting faster turnarounds, so we can start looking at, say, transmission in buses or classrooms. And then how does that feed into these models that folks who actually need to assess risk, how can that be useful for them? So before we begin, if there's any silver lining to the pandemic, it's been extremely challenging for all of us, and especially our students. But if there's any silver lining, I'd say it's been able to work with a number of my colleagues, and for the most part, for the first time, I joined Michigan as an assistant professor 5 years ago, and many of the folks I'm showing here, I've met with, and we wanted to, we had mutual interests and wanted to collaborate, and it took a global pandemic to make it happen. And so it's been a real pleasure. I'm only showing a portion of the people here that I've worked with over the last year, but really it's been quite a joy to work with my colleagues and seeing them step up to the occasion. All right, so I'm a fluid dynamicist, and I'm using this as an opportunity to discuss fluid dynamics with the broader community, and it's one of my favorite things to do. And so to begin, I'd like to say that fluid dynamics is really what controls the spread of COVID-19. And so if you want to understand disease transmission, you need to know something about the background flow. And the reason that is because the virus itself is predominantly transported by aerosols and droplets. And I'm not interested in going to debate what an aerosol or a droplet is, but they become airborne when you cough or sneeze or speak. And depending on what the airflow is doing, the airflow is going to move around those particles, and that's going to contribute who breathes in and how much. And so this is just showing a schematic from a paper came out early during the pandemic. Big droplets are ballistic. They fall to the ground. They go from one person to another nearby. The smaller aerosols tend to be more airborne and suspended for longer periods of time. What's interesting is if you look back at May, I'm talking 2 months after lockdown, there's a paper that came out identifying airborne transmission as a dominant route for the spread of COVID-19. Fast forward to about a year later, April 2021, 10 scientists' reasons in support of airborne transmission. For whatever reason, the aerosol scientists have been trying to convince the CDC and others since the beginning of the pandemic that it's indeed airborne. Let's stop worrying about wiping down surfaces. This is pretty much spread through airborne transmission. There's a number of super spreading events that support that. They can be, the virus itself is 100 nanometers, so they can stick on pretty small particles. And so it seems like it's starting to catch on, but it's been really, the aerosol scientists I follow have been really pushing this for a long time, and I know it's been frustrating for them. And so therefore, I see this as a fluid dynamics problem. But it's natural to ask, and many of us are asking this, is, well, what are my chances of getting infected, right? I gave a talk similar to this to some undergraduates, and that's the first thing they ask, am I safe? What's my chances of getting infected? Seth is going to go in a deep dive on this later in this session. And the most common approach to answer that question, and we've seen this earlier today too, is to essentially model the concentration. So this would be an average concentration, either inside of a classroom or some enclosed space. It's the concentration of, let's say, infected particles, and as a function of time. And this is going to equal we have a very simple ODE. So Q is some generation mechanism. So that's what's the rate that you're breathing out infected particles per second. And then this lambda is a loss coefficient. So there might be ventilation bringing in fresh air. There could be deposition on surfaces. There could be UV treatment to deactivate the particles. So the lambda sort of lumps all these different things that are causing the concentration to go down, while Q is causing the concentration to go up. And this is a very nice model because you can run thousands of these. It's very simple. There's an analytic solution, which is useful. So the analytic solution to this ODE is shown here. And at t equals infinity, the average concentration is simply the ratio of the generation rate by that loss coefficient. And so that's very easy to account for different types of HVAC, different types of breathing rates and so forth, get some average concentration. And then the idea, the idea then is to take that information and predict a dose. So you have concentration, you transform that to a dose, you put it in a dose response function, hand it off to someone like Seth, who's speaking shortly after me, and they'll analyze risk, right? The challenge is that this assumes the air in the room is well mixed, because the C is the average concentration. So if as I'm speaking, there are particles leaving my mouth, what it assumes is that instantaneously throughout the whole room, there's uniformly a portion of those particles fill up the room. So, as a fluid dynamicist, we know, I'll hopefully convince you that that's not indeed the case. And so this is just showing an example, and I'll come back to this later on, a study we did on one of the Blue buses. And so here we have a sick person up front, we have someone in the back, a susceptible person. There's a return in the back, so the airflow is predominantly going from right to left. And then there's supplies throughout. And what we see is that the airflow is kind of chaotic and messy. So, airflow tends to be turbulent all around us. And this concentration, so red is high, yellow is low, it's not well mixed, it's not uniform. And we can take a simulation result like this and look at the evolution of the concentration versus time. This blue is showing what a well-mixed type of model would give you, which is not unreasonable, right? It's giving you a ballpark estimate. But if we were to look at the signal of what this person in the back is actually exposed to, there's going to be a lot of variation about that. And so simply looking at the mean, I'm saying here it's not a good indicator of transmission, but that's a really strong statement. In many cases, it's probably good enough. But what I would like to know is, how good is it? When does it fail? And what is that uncertainty? And we continually see over and over and over papers published in the literature, a risk being analyzed assuming well mixed, and that's not that's for a good reason, is because the alternative is to run the very expensive simulation, and you can't do thousands of those, right? Okay, so if we want to talk about modeling disease transmission, that's the focus here. We could do that on many different scales, but I think it's important first to look at this particle size distribution. So this is the probability of a typical cough. So that when for a typical cough, you exhale about 10,000 particles. We see that the average diameter is about 10 microns. They can be as large as about 100 microns. So here we have tiny particles, here we have large particles. We'll call these larger ones droplets. And just think droplets drop, right? Those are the ones that are going to fall down under gravity fairly fast. The smaller ones we call aerosols. Where you distinguish between the two, I'm not very interested in that debate. But the idea is that from a fluid dynamics perspective, the size does matter, because large particles will be agnostic to the background flow and just have their own inertia, do their own thing. Very small particles will follow the flow, and intermediate particles will follow the flow somewhat, but they can get ejected out of these turbulent eddies and locally cluster and do some complicated things. So from a fluid dynamics perspective, if you want to know where particles go, their size does play a role. And what I'm showing here is, the virus itself is about 1/10 of a micron, so that's way down here. So that means you can stick a number of these onto these particles, right? So even a particle as small as 1 to 10 microns can hold a couple of these viruses. And obviously, the larger the droplet or particle, the more virus it can hold. And for context, 50 microns is about the width of a human hair. So everything right of that you can see, and everything left of that is basically invisible to the naked eye. So most of what expels from your mouth you can't see. So that's just giving you an idea of what leaves our mouth. So if we wanted to try to predict, where these particles go in the flow, I'm breaking this up into sort of 2 scales. One is what I call the microscale. So this would require, let's track each individual one of these particles that leave our mouth, follow where they go, and those particles are going to move according to Newton's second law of motion. So all I'm showing here is force equals ma, where the forces acting on this particle will be due to drag by the flow. So when you cough, there's a turbulent plume or jet leaving your mouth, expelling these particles, and then they're susceptible to gravity. Now, obviously, that's not going to be tractable if we want to look at transmission in a classroom or a bus. And so an alternative approach is to make a continuum approximation. So we'll say in one of our grid cells in our calculation here, we have a large number of particles, and we're going to estimate a concentration based on that. And then we're just going to treat this as basically a passive scalar and solve for the transport of that concentration. So now we don't need a resolution down to the scale of an individual particle and track each individual particle. We can just transport the concentration itself. And what I'll do in the next 5 minutes is sort of show an example of each. And so it turns out realistic coughs are sort of complicated. They're pulsatile. So this is the flow rate from a human person. You can see that there's 3 pulses within a second of a realistic cough. And we had a question, this is more of an academic exercise. If you have this pulsatile jet leaving your mouth, we thought, well, that'll lead to vortex-vortex interactions. What effect does that have on dispersion? And so I had an undergraduate and some of my grad students run these simulations. What we wanted to do is have a realistic turbulent flow leaving the mouth. So we ran this auxiliary simulation. And then what we did is we fed that into this second simulation. And this turbulent flow is now injected with particles using a size distribution informed by a realistic cough. And you get something like this. So this simulation was done on UM's supercomputer Great Lakes with 1,024 processors and required an order of days to run. These particles are bigger than they actually are, just so we can see them. But it shows you how complex the flow structure is. You get these sort of vortex rings, or you can think of smoke ring sort of formation, and particles that are emitted later on that might originate deeper in your lung and contain more virus travel differently. So this led to essentially a publication and an NSF project. But again, I see this more as an academic exercise. And if we want to start looking at decision making, we have to really go to larger scales. And so that brings us to, let's not track each individual particle, but track its concentration. And so one exercise we did was we wanted to look at the transmission on a bus. So we hired a company to come in and scan one of the blue buses. We put these sort of mannequin people in here and created a mesh. And we said, if we have a sick person in one part of the bus and a susceptible person throughout the bus, what's their exposure look like? And we can start asking questions. If you open the windows or close the windows, the airflow changes. With open windows, you get this sort of rotating flow, and which is interesting because now the people in the back are exposed to the same amount of flow. Anything that someone breathes in the front, it's not really going to reach them because they're going to be recirculated here. But what's interesting is that the return in the back of the bus is operating in such a way that if someone breathes or coughs or expels any type of particles anywhere on the bus, within about 45 seconds, everyone else is breathing it in. That's just due to the back of the envelope calculation with the volume of the bus and the airflow rate of the return. And so that's a fun fact to think about. But the big thing with open windows is it brings in fresh air, it dilutes the concentration. So we could start looking at windows closed, more people are exposed to higher concentration than windows open, for example. And then we could start looking at, well, let's come up with some thresholds. Imagine if you breathe in 1 particle, you're probably not going to get sick. If you breathe in 1,000, you probably will get sick. And so let's come up with some conservative estimate at 50, and say if you breathe in 50 particles, we'll say you're going to get COVID. Otherwise, you're not. This is somewhat arbitrary, but we can start to look at how this transmission changes when we change parameters. And so this white line is showing if no one wears a mask, and there's a sick person over here, that these are the number of people, if they're on the bus for less than 15 minutes, who's going to breathe in more than 50 particles. If only the infected person is wearing a mask, that goes way down. And if everyone wears a mask, it goes down even more. But the efficacy of the mask plays a big role. I think we're assuming 90% effective mask. In reality, it's probably 40%. And I apologize if I'm going over. The main idea here is we're moving forward with this, and we're using this code that our team's been developing to look at transmission in classrooms. We can look at the effect of what if we're a 3-foot space versus full capacity, and so forth. But what we want to do in the end is tie it back to that well-mixed model, right? Because if you want to plug this into a dose-response function and actually assess risk, we can't do a CFD calculation for every room on North Campus. And so the plan here is, let's start quantifying the uncertainty, bring in locality, look at the spatial distribution of concentration. A well-mixed model will tell you it's a delta function. You have one value of the mean, but the CFD will give us distributions. And we're hoping to augment or add corrections to these well-mixed models so we can, it might be on average, your risk is low, but if you're standing right next to someone who's sick, your risk is quite a bit higher. So how do we incorporate that locality into the model? And that's what we're really focused on right now, and working with a number of experimentalists and other modelers to address the transmission in classrooms. And with that, I apologize if I'm talking super fast, but I think I'm at 16 minutes and happy to take any questions.
Thank you. That was very interesting. So I don't see any questions in the chat, but I have a question for you. So, so much this has been such a focus of debate, this idea of how close is too close and how far is far enough away, kind of based on these previously pretty arbitrary 3-foot, 6-foot types of definitions. What do you think that we have the tools to answer those questions? Like, do you think that?
Oh, sure. Yeah. I mean, the 6-foot rule came about, my understanding is from a German study in the late 1800s. And then there's some work by Wells in the early 1900s. And clearly the idea then was you breathe out particles, the big ones fall, the small ones evaporate, and 6 feet, they fall within 6 feet, you're fine. But in reality, you're breathing out this moist, turbulent plume. And so the evaporation's hindered. And there's been really nice studies from MIT where they have a well-controlled experiment of someone coughing, and with no background flow, the cloud of particles can travel 24 feet. And we know if you're indoors and there's heating and air conditioning, really what it comes down to is social distance means there's less people in the room, which means there's less likelihood that someone sick is in the room. You can't discount the fact that if someone right next to you sneezes on you, right, now you're breathing in a large portion of that, right? So that is indeed important. But when you're indoors, like what I said on the bus, within 45 seconds, you're breathing in what everyone else is breathing out. That's just due to the airflow. And so social distance doesn't really matter. What matters is how long you're on the bus and how many people are on the bus, right? And so, yeah, I think it's pretty well known. 6 feet is somewhat arbitrary, but it's not straightforward, right? I mean, distance plays a role to some extent at the same time.
Well, I like that way of looking at it, that it's dedensification and distance. Yeah. Excellent. So thank you very much for that wonderful presentation.